So, coming from a heavy equipment and hydraulics background, I get a lot of questions about hydraulic systems. How do they work? How do we best diagnose them? What are they all about? And so, I finally decided to just go ahead and do a basic hydraulics class. Nothing crazy, nothing in depth, nothing super technical. Just what you need to know to be able to apply hydraulic theory and diagnostic principles to your daily job. So that's what we're going to get into. It's going to be a multi-part series. We're going to start with the intro today. We're going to get into individual components, how they work, then schematic symbols, then putting those schematic symbols into reading an actual schematic, then applying all that knowledge to diagnosing various hydraulic systems. So if we switch over to the PowerPoint, what we have here is a very, very super common hydraulic pump. In this case, this is what's called an rotary piston pump. Works very much the same way as an internal combustion engine with some differences. Right here, you've got your barrel. Looks a lot like a revolver barrel. You've got your pistons here. So your barrel is similar to your engine block, and your pistons are very similar to your regular pistons. Some differences you'll notice here are the slipper right here and your slipper plate. And then this here would technically be considered your drive shaft. So you're still compressing, you're inhaling, exhaling, okay? Very similar to the internal combustion engine. In this case, you're sucking and pushing or pumping fluid. So that's what we're dealing with. How are we taking motion from something we understand, an engine in this case, or a brake booster, a pump, whatever it may be, and using that fluid to perform work? So, where are hydraulics? Where do we see hydraulics other than heavy equipment? And let's be honest, we all see hydraulics in almost everything we do every day. We just don't realize it, or we're not using the same terms we're used to using to describe them. So we see them in fuel systems, automatic transmissions, cooling systems, braking systems, steering, the lifts we use in and out every single day to service these vehicles, the jacks we use, and of course the conventional ones, the heavy equipment. Most basic concepts of hydraulics. Really, if we were to distill it down to the essential concept and what we're really doing, we're using a small force to generate a proportionally larger force, generally an exponentially larger force. We have to understand that liquids are essentially incompressible, meaning when we try to compress fluids, they don't compress like air does. They don't get tighter, they don't get smaller. The force we put on them is applied elsewhere in the container. We have to understand the basics of Pascal's Law, just the same way we have to understand the basic of Ohm's Law, Kirchhoff's Law, Boyle's Law. We don't need to know every single theoretical mathematical equation. We just need to understand enough of it to be able to apply that to what we're trying to do. We need to understand the difference between pressure versus flow and how they are generally inversely proportional. As pressure increases, flow generally decreases, and vice versa. There are exceptions to the rule, as there are exceptions to pretty much every rule, but in general, pressure increase, flow decrease. The difference between pumps versus motors versus pump motors versus linear actuators versus rotary actuators versus selective control valves, proportional control valves, solenoid activated control valves, high pressure reliefs, low pressure reliefs, case drains. They're all a lot of terms you may not all be familiar with, but it doesn't need to be that intimidating. There was a time when each one of us didn't understand the difference between a relay and a switch and a transistor and a diode and a diode versus a Zener diode. MOSFETs, it's the same thing. It's terminology we need to learn at least enough to know what it's describing. And going to catch some flack for this, but it's like electricity, but it's not. You'll often hear teachers explain electricity using hydraulics or hydraulics using electricity, and they do share some common concepts. A lot of different components of them can be compared to each other, but I feel that it's a bad habit to get yourself into to apply rules of electricity and concepts of electricity to hydraulics and vice versa. I find it can trip you up in the long run, and it's better to treat it as its own separate entity. That's my opinion. Others may disagree, but that's how I feel it's best to handle it. So the simplest hydraulic system I can think to explain to you guys is the same hydraulic system we've all dealt with in one form or another. A regular pump jack, a bottle jack, a floor jack, and you take a smaller piston and you pump it, generally with a longer stroke, meaning our floor jacks, our bottle jacks, we have a lot of stroke here for a little bit of movement on the lifting end. What we're really doing is we're taking a very small area and we're attempting to compress that fluid. The fluid does not compress, and so it takes the force we're generating here, pushes it through the system up onto a larger diameter piston, which then magnifies the force and gives us our lifting. Now, we may have, say, 6 inches of stroke here. Because we're going from a smaller diameter to a larger diameter, we're going to cut down our stroke. And there's math involved in that, and we'll get into how much of that we really need to understand and when it makes a difference. But suffice it to say, if we have a long stroke here, as we magnify that force, we decrease the overall stroke. So Pascal's Law, that's going to be something that we need to learn, as I said before, just like Ohm's Law, Kirchhoff's Law, Boyle's Law. Need to learn it at least enough to apply it. And the math. I know, it sucks. So I'm going to have to ask you guys to all do some physics equations here and some fluid dynamics modeling. But you'll see in the screen here, we've got our input force and our output force where there's a multiplication of force, right? We've got all these fun variables. We've got distance, we've got diameters, we've got subsets, superscripts, the whole 9 yards. Biggest thing to keep in mind, right here. You have to pay for the multiplied output force by exerting the smaller input force through a longer or a larger distance. Like I said, long stroke on the jack handle, short stroke on the lifting side. So Pascal's law really boils down to P is equal to F divided by A, where pressure is P, force is F, area is A. So generally, we know what pressure we're going to want, and we can calculate our force or our area. Most of the time, we don't even have that information, at least in an automotive aspect. Medium duty, heavy duty, off-road, a lot of times we do have that spec and we can calculate that. But what we need to know is, much like Ohm's law, as we have any one variable, we can figure out the other two. So we know that if we increase our pressure, right, we want more pressure and we retain the same area, what's going to have to happen to the force? We're going to have to increase the force to increase the pressure if we're working on the same area. And there's a few of those, and we'll break that down in its own separate lesson, but it works much the same way as Ohm's law does, just using different variables and different concepts. So pressure changes anywhere in a sealed fluid system are transmitted without any loss in a perfect environment to all of the fluid within the system. Now, we're going to have pumping losses. We're going to have friction losses due to the tubing and the diameters we're using and overall components, environmental aspects. But really, in a wide open system like we have here, where you have one piston directly acting on another with no valves, no orifices, no relief valves, anything, that the pressure we exert on the left-hand side here is going to be the same pressure we exert on the right-hand side, and the force is magnified because we're exerting the same pressure over a larger area. Any pressure exerted on a closed system is transmitted equally, as we discussed before, and at right angles to all parts of the container. Very wordy. Basically, once again, it's going to equally distribute throughout the system, but it's also going to go in all directions equally. So pressure is essentially, to steal a term that isn't the best to use here, but to use one you guys are all familiar with, the pressure becomes stoichiometric in a way. It's equal throughout. It's at the perfect rate where every part of the system is seeing exactly the same pressure. If there's pressure differentials, it's either intentionally engineered in or there is a fault causing that pressure differential, and that would be an increase or a decrease above system pressure where you don't want it. Pressure applied to any part of the system will be transmitted equally in all directions. So we've said the same thing 3 different ways, kind of. What we need to think about now is this. If I'm exerting the same pressure here, because I retain the same force, I have the same area of the piston, and so I have a set pressure, we'll call it 100 psi, coming up here. All parts of the cylinder here and the piston seals are all under 100 psi worth of pressure. All right? Now, say I've got a little nick in the seal here. Well, that 100 psi is going to be shooting out here as well because it's enacting the same pressure on all parts of the system. So if we have a little nick, now we're shooting 100 psi worth of fluid pressure out here. That's going to reduce the overall force we're able to apply here, or we can apply it, but we may not be able to retain it because that pressure is leaking by. And if we leak by some pressure, we're going to drop down. Simplification again. Gases, super easy to compress. That's how internal combustion engines work. We know we can compress gases. That's why we have compression ratios. We've got 9.5 to 1. We've got 24.5 to 1. We've got 16.5 to 1. Whatever it may be, we can compress gases. Refrigerant systems, we're compressing gases. We know how they react. We know what's going to happen, and we know we can compress those gases with very little effort. Solids, on the other hand, are very hard to compress, right? That's why we have shop presses, we have air hammers, we've got BFHs, because solids, you can't just squash them down nice and easy and have something happen. So we have to exert force on them because they're relatively solid, and we got to press an axle out of a hub assembly, right? We start applying that hydraulic ram from the shop press on it. The end of the axle doesn't just start compressing and blobbing out. No, we need to put quite a bit of force on it and probably quite a bit of heat to get it to do that. So we understand that solids more directly transmit force without compressing. Hydraulics and fluids, they're kind of a hybrid. You can compress them slightly depending on the fluid, but not really. But in some ways, they also act as a gas. So they're a hybrid between a gas and a solid, and so they have their own little rules and their own little applications. That's why we call them virtually incompressible. Once again, pressure is the force acting on an area. So P is equal to F divided by A. We remember that equation. We input whatever variables we know, we can figure out the rest of the equation. Small force on a small area in a closed system will then generate a larger force on a larger area if it's able to access it. This is called force magnification. We magnify the force. So how can I use this? Say you got an intermittent overheating condition in a cooling system, right? You've replaced the thermostat, maybe you've done a coolant flush on the system, maybe you've replaced some hoses, you suspect a blockage, right? By understanding fluid dynamics, hydraulics, and how fluid reacts in different flow conditions, in different pressure conditions, in different restrictions and heats, we can really start to narrow down using temperature sensor readings, be them directly from a sensor, be it through scan data, be it through infrared thermal imaging, or even the hand test. Grab hold of it, too hot to touch, too cold to touch. We can start to use this knowledge of fluid dynamics in order to pinpoint or get as close to a pinpoint test to figure out what we need to do. Transmission faults with and without circuit codes. So I had a Silverado with a 6L80E transmission not that long ago that would shift fine all day long at elevated RPMs. You were rolling down the road. It was great. 1,500 RPM to 1,200 RPM. Torque converter lockup going down the highway. You'd have the old rumble strip torque converter fault. That was one indication. Second would be when you would stop at a light after about 3 to 4 seconds at regular idle, which was about 720, 750 RPM, the transmission would essentially neutral out and you would have to tack it up to almost 1,1600 RPM to have the trans engage again, and it was like dumping a clutch. It was bad. All that, along with the fact that pressures were good in scan data, we didn't see any mismatches, anything else, led me to believe a low-speed fluid flow condition from the transmission pump. I was able to come to that conclusion through a combination of service info, readable data, actual pressure testing, and understanding how hydraulic systems work. We make a lot of hydraulic calls, a lot of transmission calls, where we can only see so much. Maybe we don't fully understand every little check ball valve, everything within a transmission, and we send it out to the builder. The builder goes over the whole transmission. They think they found everything, but they can't dynamically test it as well as we can. If we understand hydraulic systems at a higher level than we currently do, we can, number one, diagnose a transmission issue a lot simpler, but we can also help that transmission rebuilder if we're not doing it in-house, if we're not getting just a off-the-shelf reman. We can kind of work with them and help both of us to pinpoint where we're looking, what we're concerned with. Engine lubrication systems. Oil pressure. Not super complicated in most engines, but it's something to keep in mind, and it also plays into certain fuel systems. Without good engine lubrication systems, without good pressure, without proper flow, some fuel systems don't work properly. Braking issues, correct length of brake lines, a ABS valve, solenoid valve that's shifting too quickly or too slowly or not fully shifting. We can run into issues there, where traction control systems don't work properly, where we have on-one wheel lockups, where we have a lot of issues. Understanding hydraulic principles helps us better diagnose these. Fuel systems. So if a lot of you aren't familiar with diesel fuel systems, one that's been around for a long time, the venerable 7.3 Power Stroke is one I love using as an example. Used HEUI systems, hydraulic electric unit injection. So they take low pressure oil from the engine that feeds into a high pressure oil pump, which then uses force magnification, uses the fact that fluids are virtually incompressible, and attempts to compress them, which exerts a larger force, multiplies the pressure. So you go from a base engine oil pressure of 40, 50, 60 psi to 1800 psi, right? That high pressure oil is then used to fire another plunger working on the hydraulic principle. That 1800 psi acting on a large piston then fires off fuel to an even higher pressure because it's on the smaller side of the piston, allowing us good injection, allowing us good flame front propagation, allowing us low engine noise, lower emissions, higher power, more reliability. So once again, understanding basic hydraulics, we can diagnose engine lubrication, we can diagnose low pressure oil, we can diagnose high pressure oil, which we can then use to diagnose the base injection system, as well as diagnosing the low and high pressure fuel systems, all with some very basic concepts. Steering issues, hydro boost issues, PTOs if you have tow trucks at your shop, if you work on them, if you work on dump trucks. The conventional hydraulic systems we see in skid steers, excavators. There's an excavator right now digging out the Suez Canal. Lone little excavator, tiny little thing, doing all sorts of crazy work based off of the fact that basically Pascal's Law allows a very, very small machine to do some very, very big work, not factoring in leverage with longer dipper arms and everything else, but you can do a lot with a very basic equation. Force is equal to pressure divided by area. It's pretty cool, at least to me. Your parts washer, your pressure washers, your home plumbing, they all run off of these fluid dynamic principles, and they're not overly complicated. We can learn a lot, we can apply a lot, we can do a lot, understanding basic concepts. So, my big thing has always been and will always be, if we learn the basics, the concepts behind things, we can then apply that to broader and broader and broader concepts and become better at our jobs, become more efficient, more proficient, and it benefits us, it benefits the shop, it benefits the customer. We all win. Plus, we don't get our butts kicked nearly as much as we may have before if we skimmed over it, we thought we understood it, we applied rules of electricity to rules of hydraulic, whatever it may be. So, hopefully this will be a series that everybody gets interested in. We'll be going through components, schematic symbols, schematics, applying all that info just like you would electrical systems, applying all the hydraulic info to diagnosing and troubleshooting systems as easily as possible. And my number one thing, not only easy, but as much by the seat of your pants as possible, meaning sitting in the driver's seat, sitting there using the easily available data before you start cracking lines, getting adapter fittings, putting pressure gauges on, which there is a time and place for it. But those who have done hydraulics know it can get messy, it can get frustrating, and you don't always have great specs. So, it's been a long day. It's been a long weekend. We'll go from there. I got to get some sleep, and I will catch you all later.